force vector, you can do better vector, force vector along, you can write it that along a line. Right, so we have a line, we know 2 points. If you know 2 points, you can write the equation for a line between those 2 points, and we want to find the vector passing those 2 points. So in 3D space, the direction of, let's say, of a force or of a vector generally, but in this course we are mainly talking about force when we talk about vector, of a force is or can be specified, can be specified by 2 points. 2 points through which, you can write it this way, through which its line of action passes. So line of action is a kind of new term that you see here. If you think about the force as a vector, a line of action is the line passing that force is collinear with, right? If you think about a force vector like this, right, this would be your line of action. This would be your line of action. If you have your force vector in this way, the reason I explain line of action, because you're gonna hear this term again. This would be the line of action. So the line of action for a force, right? So what is here saying is that if you can basically represent a force or specify a force for 2 points, that the line of action of the force passes through those points, right? An example, I do have an example. I put some figures there. If I can, that's not, again, I'm working on setup. Bear with me. There you go. It's an example of a simple situation that you can think, right? Imagine that you have a point here. Let's say this is point, let me use a bit of color. So this is point A, and this is point B. So the force in this cable or chain holding this ship, the line of action of this force is this. This is the line of action. If this is your cable, then you have your line of action along the force. The line of action is straight. That's as straight as I can go. Very bad straight. Okay. From A to B or from B to A. Right? So in this case, we said, well, let's look at the part that the cable is connected to a ship. So A to B, this is line of action. And if you know the coordinates of A and B in some coordinate system, depending on where your coordinate system is, let's say your coordinate system is somewhere right here, X, Y, and Z. If you know the coordinates of A and B, you can write, you can represent this force in three-dimensional space. How do we do that? Well, let's say A has the coordinates of XA, YA, and ZA. And B has the coordinates of XB, YB, and ZB in three-dimensional space, right? Somewhere in 3D space, we can represent this X, Y, and Z, A and B, knowing these three coordinates. So R, vector R, going from A to B, if you want to represent the vector R, you can just think about it as a vector going from A to B, is whatever is the coordinates of B minus whatever is the coordinates of A, right? It would be XB minus XA I plus YB minus YA J plus ZB minus ZA K. So if you think about I, J, and K as coordinates, as let me change this. Give me a second, folks. I just wanna. All right. All right. All right, I guess it's as good as it gets. All right, so if you think about A and B with X or Y and Z coordinate for each one, it represented that, right? And this is the vector R, but this is the vector R, position vector R, position vector R from A to B. Right? It's going from A to B. So XB minus XA, YB minus Y. Now, once we know this position vector, which we can easily find knowing the coordinates, right? We can calculate the unit vector. From a unit vector would be unit vector U would be whatever is the R vector divided by magnitude of R. If I go back, let's see if I can find it here, if we define it here. There you go. So unit vector, remember, this is what we talked when we talked about unit vector, right here. We said unit vector, right here, is the vector divided by the magnitude of the vector. And that's what we're doing here. So I'm defining the unit vector along force F going from A to B by just dividing the vector R as the vector representing this direction by the magnitude of the vector R. So if you do that, here is what you get. You'll get, well, whatever is X, so you'll get XB minus XA divided by, or let's do everything together. The magnitude of R would be square root of, maybe I need more room. Square root of XB minus XA squared plus YB minus YA squared plus ZB minus ZA squared. This is the magnitude of the vector. Again, this is what we introduced before. Going back to what we did, right? The magnitude of a vector right here. We said is A is equal to AX squared plus AY squared plus AZ squared. In this case, components are xb minus xa, yb minus ya, and zb minus za. The vector and whatever is the vector, so this would be xb minus xa. That's not what I wanted. Xa I plus yb minus ya j plus zb minus za k. So once you know the unit vector, going back again, this is what, here is what we can do. We can say, well, if we know the unit vector, the vector f is the magnitude of f, whatever is the force, magnitude, 10 newtons, 20 newtons, 400 newtons, multiplied by the unit vector. Here it is. We said the vector can be represented by as its magnitude multiplied by the unit vector in the same direction. So here is what I'm going to do. Going in the wrong direction. Here's what I'm going to do. Let's say, well, therefore, for f, right, as a vector, is the magnitude of f multiplied by unit vector u. This is what you need to know. All right. This one and this equation, you're going to use it a lot. Let me see if I can clean this up here. So the only equation is in there. Go. This is the equation that you need.